All right, so in the last lesson, we looked at the reciprocal identities, quotient identities, and Pythagorean identities. We're going to carry on with some other identities, the sum identities, the difference identities, and the double angle identities. And these ones all have to do with adding or subtracting numbers within the argument of your sine, cosine, or tangent functions. So here's the sum identities. Sine of a plus b equals sine of a times cosine of b plus cosine of a times sine of b. Notice how the arguments in cosine and sine swap there. Cosine of a plus b is cosine of a times cosine of b minus sine of a times sine of b. And tangent of a plus b is tangent of a plus tangent of b over 1 minus tangent of a times tangent of b. Okay, these are called the sum identities. I'm not going to prove them, but if you want to see the proof, you can go to page 290, whoops, not 99, page 299 in the textbook, and you can see the proof there. Now, just to make sure that we're clear on what this means, if we take the sine sum identity, for example, I'll just copy it out down here. If you have two different angles, A and B, and you add them together, then you have this identity. So for example, let's just suppose we take an example of A is 10 and B is, I don't know, 15. Okay, so then that tells us that sine of 10 plus 15, 25, is equal to sine of 10 degrees cosine of 15 degrees plus cosine of 10 degrees times sine of 15 degrees. That's what the sum identity is really saying. That this here can be split up and placed as so. In fact, we could split it up in another way. We could also say that sine of 25 degrees is something else here. If we wanted to split it up as, say, 5 and 20, right? So we could say sine of 25 degrees is the same as sine of 5 degrees cosine of 20 degrees plus cosine of 5 degrees sine of 20 degrees. Okay, so I just want to make sure you're clear on what it's actually saying here, that two numbers added together make the argument on the inside of sine, and then each of those separately get put into these different places to make the identity. All right, so those are the sum identities. Now, following up on this, we have what are called the difference identities. And the difference identities are really quite simply all of the sum identities with the signs switched. So this plus becomes a minus, this plus becomes a minus. This plus becomes a minus, this minus becomes a plus. This plus becomes a minus, this plus becomes a minus, and this minus becomes a plus. And then you get your difference identities. So these are the difference identities, and as I said, they're just the sum identities with all the signs switched. So instead of plus, 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 we have minus, 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 here, here, and here. And instead of adding for the sine and subtracting for the cosine, we subtract for the sine and add for the cosine. And instead of having plus in the numerator and minus in the denominator for the tangent sum identity, we have minus in the numerator and plus in the denominator for the tangent difference identity. Okay, so three more identities very similar to the previous ones. Now the proof here is to prove the difference identities based on the sum identities is really not so difficult. I'll just sketch the proof really quickly. I'm not going to do a full proof, but the idea here is if you have sine of negative x, this is identical to negative sine of x. Okay, and I'll show you that in a second. And if you have cosine of negative x, this is identical to cosine of positive x. Okay, and to see these two things, I'll quickly show you on Desmos. So let's do that. Cosine of negative x and cosine of positive x are identical first. Here we have cosine of x, of positive x. Now, if I put a negative there, that means that my b in my transformation is negative 1. And so a b of negative 1 means that I flip this, I reflect it over the y-axis. But if you look at it, if I flip this over the y-axis, I don't change it at all. Right? You can see I can add and subtract a negative there, and the graph doesn't change one bit. Y equals cosine of negative x is exactly the same, and the reason is because reflection over the y-axis does nothing. So that gives us the identity that cosine of x equals cosine of negative x, which we'll use in just a second to prove the difference identities. Let's get that sine of negative x is the same as negative sine of x. This one's a little trickier to see, but it's not so bad. So let's just get sine of x first. Now, sine of negative x means I'm going to reflect over the y-axis. So here it is, sine of negative x. There it is, reflected over the y-axis. But you can see pretty simply from this picture that reflecting over the y-axis is identical for sine as reflecting over the x-axis. Right? So in green, I've reflected over the x-axis. In blue, I've reflected over the y-axis. And you can see that, in fact, the green and the blue are identical to each other. Okay? So those reflections are identical when it comes to sine. And so that tells us that sine of negative x equals negative sine of x. All right. Now you might be thinking, okay, Mr. Jones, I understand to this point, but what's the point in this? How is this relevant? Well, let me show you. If we come back over to our identities here, I want to prove each of these difference identities based on the sum identities. Okay, so the first one, we have a sum identity of sine of a plus b equals sine of a cosine of b plus cosine of a sine of b. Okay, so what I'm going to do is to create this, I'm going to say, okay, b becomes negative b. Or you might prefer it if we give it a new letter. Let's change it to the letter D, okay? B is going to be replaced with a negative D. That's how we get a negative, so that we're adding a negative. That's the same as subtracting a positive. That's how we can get this here. Well, if I replace B with negative D everywhere, I'm going to replace this B with a negative D. I'm going to replace this B with a negative D. So I have cosine of negative D, but we have that the cosine of a negative is the same as the cosine of a positive. So this negative has no effect. It's just the same as cosine of positive D. Here, when I replace sine of B with sine of negative D, we can see that this has the same effect as a sine of D made negative times a negative 1. And so when I have cosine of A times sine of negative D, that's the same as cosine of A times sine of D times negative 1, which makes this plus a minus. And so I'm left with sine of A cos of D minus cos of A sine of D. Or if we want to replace our D back with the letter B, we get this formula here. Okay, now if you don't quite follow the proof, it's not a big deal, but that's how the proof works. I can do the same thing here with cosine. Originally we had cosine of A plus B is cosine of A cosine of B minus sine of A sine of B. I'm going to replace my b's with negative b's. When I replace this b with a negative b, I get A minus B. When I replace this b with a negative b, I get cosine of negative b. But we know that cosine of negative b is the same thing as cosine of positive b, so that has no effect. When I replace this b with negative b, I end up getting sine of negative b. But we know that the effect here is the same as bringing that negative out. So this is the same as sine of A times sine of B times negative 1, and minus a negative is the same as a plus. And there we go. We've just derived it. We've just proven that one. Exact same thing for tangent. You can go through the exact same argument to prove the difference identity there. So now this brings us to the double angle identities. Here they are. Sine of 2 times an angle equals 2 times sine of the angle cos of the angle. Cos of 2 times an angle is 2 times cos of the angle squared minus 1. Or equivalently, 1 minus 2 times sine of the angle squared. And tangent of 2 times an angle is 2 times tangent of the angle over 1 minus tangent of the angle squared. And just to make sure we're clear on what's going on, if we have sine of, for example, 60 degrees, this is 2 times some angle. So my A in this case would be half of 60. A is 30, because 2 times 30 is what gives me 60. So this is saying that sine of 60 equals 2 times sine of 30 times cosine of 30. Okay? That's what the double angle identity is saying. And in this specific case, actually these are special angles, so we could actually verify it. Let's go ahead and do that. In fact, pause the video here, see if you can verify this double angle identity. Or if you prefer, take cosine of 60 and see if you could verify that one. Okay, so I'm going to do it. Sine of 60, we know is root 3 over 2. We've memorized that. It's a special angle. 2 times sine of 30, we know that that's a half. We've memorized that. And cosine of 30, that's root 3 over 2. We've memorized that. Are these two sides equal? Yeah, of course they are, because 2 times a half cancels out. We get root 3 over 2 equals root 3 over 2. So that's kind of nice. But just by the way, historically, where this came in really handy was in being able to derive the sine and cosine and tangent of angles that are not special angles. Because all of a sudden, we have a relationship between an angle and half of it. And we also have relationships between differences in angles. I should just fix this up and put a B. Okay. In any case, these are the double angle identities. Now the proofs are pretty straightforward based on the sum identities. So for example, if I take sine A plus B equals sine A cos B plus cos A sine B, okay, that's the sum identity. To get this one here, all I have to do is say, okay, let's let B equal A. And substituting A in for B, we get sine of A plus A equals. So if we let b equal a, then we get sine of a plus a is sine of a cosine of a plus cosine of a sine of a. So in other words, sine of 2a is sine a times cos a plus another sine a times cos a. So that's two groups of sine a times cos a. And there we have it. That's the proof. We have the double angle identity for sine. Let's also prove the double angle identity for cosine. And again, it comes from starting with the sum identity. So cosine, let's get another proof. Cosine of a plus b, we know is cosine of a cosine of b minus sine of a sine of b. And what I'm going to do here is I'm going to let b equal a again. So I now have cosine of a plus a, that's 2a, is cosine of a cosine of a minus sine of a sine of a. So I have cosine of 2a equals cosine of a squared minus sine of a squared. And you know what? I didn't actually include that one. Oh yeah, no, of course I did. Okay, we're all good. So cosine of 2a is cosine of a squared minus sine of a squared. Yeah, no, I didn't include that one right up here. I should have added. We have this common identity, this common identity, and we have the cosine of a squared minus sine of a squared common identity. Cosine of 2a equals all three of these, whichever one you please. Okay, so we've just got this one here. And to get the other ones, we just use the Pythagorean identity. So remember that sine a squared plus cosine a squared equals 1, right? So that means if I subtract cosine a squared on both sides, that sine a squared is 1 minus cosine a squared. And so this can be replaced with this. And that will give me this one right here. So let's go ahead and do that down here in the proof. So we've got our first one. And now to get another one, I'm going to replace this with 1 minus cosine of a squared, right? Because I'm going to remember over here on the side that sine of a squared plus cos of a squared equals 1. So cos of a squared is 1 minus sine of a squared. That's what I have right here. And so this works out to cosine of a squared minus 1 plus cosine of a squared, which is two groups of cosine of a squared minus 1. That is this form right here. Okay, so we've proven that one too. And to prove this last form right here, same exact thing. This time we replace cosine of a squared with 1 minus sine of a squared, because cosine of a squared is 1 minus sine of a squared. So let's do that down here. I'm going to write that cosine of 2a is cosine of a squared minus sine of a squared from this line up here. Okay. And I'm going to replace the cosine of a squared with 1 minus sine of a squared. So this is 1 minus sine of a squared minus sine of a squared, which is the same as 1 minus 2 groups of sine of a squared. There we go. That's the third one. So now we could also prove the tangent double angle formula, again using the sum identity. I'm not going to do that one here. If you want, you could try that one out. That would be good practice. And there we have it. So we have now 3 sets of new identities: the sum identities, the difference identities, and the double angle identities. And in the case of the double angle identities, we have 3 different forms that we like to use for cosine of 2a. All right, now what do we do with all these identities? Well, we use them to make simplifications. So I'll go through 4 examples here. The first one is to simplify 1 minus cos 2x over sine 2x. And of course, get the restrictions. Okay, so I'm going to actually start with my restrictions. For my restrictions, I have that this denominator can't be 0. Okay, so sine of 2x cannot be 0. And the numerator is okay. There's no issues there because cosine of 2x is defined everywhere, right? Just like 2x could be a. So cosine of 2x is cosine of a. It's defined everywhere. There's no problems here. 1 minus it, defined everywhere. There's no problems. I'm not dividing by 0 up in that numerator. The only issue is that this denominator can't be 0. And when would this be 0? Well, it's kind of neat. There's actually a couple ways to solve this. Let's solve it the most straightforward way. Let's say if we let a equal 2x, then we're saying that sine of a can't be 0, okay? And let's get the restrictions over one circle. We're going to go over one revolution. X is between 0 and, let's work in degrees for the moment, 360 degrees. So that means that a is going to go from 2 times 0, that's 0, up to 2 times 360, that's 720. Okay? So in order to get the restrictions of one circle worth of a, we have to actually go 2 circles worth, sorry, 1 circle worth of x, we have to actually go 2 circles worth of a. Okay, so now a then, 2 revolutions, sine looks like that, that's 360, sine looks like that again, that's 720. So a can't be 0, it can't be 180, it can't be 360, it can't be whatever that one is there, I guess for 540. Okay, and it also can't be 720 right here, but we don't have an equal sign. So in fact, we don't need to include the 720 because we're technically not going that far, because we're not going to include the very end point. So that's what a can't be. And since a equals 2x, or in other words, x equals a over 2, this gives us what x can't be. X can't be 0 divided by 2. X can't be 0. X can't be 180 divided by 2. X can't be 90. X can't be 360 over 2. It can't be 180. And it can't be 540 over 2. It can't be 270. Okay? So those are our restrictions on x. Now, we've got our restrictions. Let's do the actual simplification. We have this expression, and we would like to simplify it. So I'll work down here, 1 minus cosine of 2x over sine of 2x. Now, sine of 2x only has a single identity to use. So that's pretty straightforward. I'm going to go 2 sine of x cosine of x. Cosine of 2x has 3 possibilities for what to put in here. I could put in, cos x squared minus sine x squared as one of the identities. Let's just look up here. Right? We have cos x squared minus sine x squared. That's 1. But that one's not going to work out so well, because in my numerator, I'm going to have 1 minus cos x squared, plus sine x squared. It won't cancel with anything. So that's not likely to work out so well. What else do we have? Well, cos 2x is also equal to 2 cos x squared minus 1, or 1 minus 2 sine x squared. Now, let's see here. If I put the identity with a 1, then I'm going to have a 1 minus a 1, and those are going to cancel out. This seems right to me, because the more canceling, the easier it likely is to have a simplification. So I'm going to choose this identity here. The cosine 2x is 1 minus sine x squared. That now simplifies into 1 minus 1 plus sine x squared over 2 sine x cos x. And this simplifies to sine x squared over 2 sine x cos x. What else could we do here? Well, here we have sine x times sine x, right? If you prefer, I might as well go nice and slow here. This is sine of x times sine of x. And in my denominator, I have 2 times sine of x times cos of x. Well, clearly I can divide the numerator and the denominator both by sine of x. What am I left with? Well, there's a few different ways we could do this. I prefer to say, look, this is the same as 1/2 times sine of x over cosine of x. And what's that? Well, that's tangent. There we are. So we have that 1 minus cos 2x over sine 2x is in fact the same thing as 1/2 times tangent of x. That's pretty nice. And of course we have our restrictions. If x is going to be around one circle, we get that x can't be 0, 90, 180, or 270. Okay. Or if we want to have a general form for this, we would say we have 1/2 tangent of x. And in general, x cannot be any multiple of 90 degrees. So I would say x can't be 90 times n degrees, where n is an integer. This will cover all of the multiples of 90. Or some people might prefer to write n times 90 degrees, like that. I think 90 times n degrees is just fine. So there we go. That's our answer. Now you can go ahead and try this one. I'm going to give you something quite similar. Sine, so simplify and find the restrictions of sine of 2x over cosine of 2x plus 1. Pause the video, try that, and when you're ready, unpause and see if you got the same thing as me. Okay, so first, this time, I'm going to actually do the simplification. I'll do the restriction second this time. Sine of 2x is clearly 2 sine x cos x. There's no choices there. Cosine of 2x, I have 3 choices. I can have cosine x squared minus cosine of x squared minus sine of x squared. Excuse me. I can have 2 cosine of x squared minus 1. That's the one I'm going to choose. Or I could have 1 minus 2 sine x squared. Now, why am I going to choose this one here? Well, because just like last time, I'm going to have a minus 1 and a plus 1. Those will cancel out. That's going to make things simplify more nicely for me. So now I have 2 sine of x cosine of x. In the denominator, I'm left with 2 cosine of x squared. That's 2 times cosine of x times cosine of x. I can divide top and bottom by 2. I can divide top and bottom by cos x, leaving me with 1 cos x in the denominator. And so I have sine of x over cosine of x, or in other words, tangent of x. Now for the restrictions. Well, I can't have this denominator equal to 0, which is identical to this denominator, which is identical to this denominator. So in other words, cosine of x squared can't be 0. How could you ever have cosine of x squared equal to 0? Well, the only way for this to be 0 is if cosine of x is 0. So that's my restriction. Cosine of x can't be 0, which I also have right here. Can't be 0. Now, that's pretty easy because we know that cosine of x is 0 at 90, 270, and so on, or pi over 2, 3 pi over 2, and so on. All the odd multiples of pi over 2. So I would say that my final answer is tangent of x, where x is not pi over 2 or 3 pi over 2 if I just use one revolution around the circle. Or in more general terms, I want to say that tangent of x is my answer, my simplification, but x cannot be pi over 2 plus any addition of a multiple of pi. If you walk through the different values of n in the integers, you'll see that this expression covers pi over 2, next 3 pi over 2 when n is 1. When n is 0, we get pi over 2. When n is 1, this works out to 3 pi over 2. When n is 2, this will work out to 5 pi over 2. And so, in fact, in general, that's our solution there. Okay, now I should correct myself. I found an error in this example here, the 1 minus cos 2x over sine 2x. Quite simply, it is right here. I forgot that the identity is to subtract 2 times sine x squared. Okay, so this becomes a 2 sine x squared. And so then on my simplification here, I end up canceling out the 2. Right? I cancel out both 2's. And so in fact, this is not 1/2 tangent x. It's just tangent x. Okay. So sorry about that. I missed that. This is why, when you're on your tests, no matter how well you know your identities, you should still look at the formula sheet if you have an identity on there, just to double check, make sure you're getting it right at every step. All right, let's do another example here. This time, I'm going to do a question that says, find the exact value of sine of pi over 12 without a calculator. Okay, this is kind of cool because with this question, I'm showing you how we can get exact values of trig ratios of angles that are not special angles. This is actually giving you a little insight into how these tables were derived and then later in history programmed into calculators once calculators were invented. But of course, trigonometry has been used for hundreds of years, well before calculators and computers were invented. Okay, so I want to find this exact value. What I want to do is I would like to use either sine of a plus b, sine of a minus b, or sine of 2a, where I'm representing pi over 12 in one of these other ways, and the a and the b, or just the a, are special angles that I can evaluate. Okay? So I have to think, how could I combine some special angles to get pi over 12? What are the special angles? Well, 0, which isn't going to be very helpful in this context. 30, which is pi over 6. 45, which is pi over 4. 60, which is pi over 3. 90, which is pi over 2. That's what I'm working with. Okay? So how could we use a couple of these to get pi over 12? Pause the video and think about it for a sec before I give you an answer. Okay, now you might be tempted to say, oh, well, pi over 6. Pi over 12 is pi over 6 divided by 2. We can use this one. Well, that's true, but it's not actually so good, because that would be saying that we have sine of pi over 6, which, yes, is a special angle we can get, equals 2 times sine of pi over 12 cosine of pi over 12, and now we're stuck, because this is the thing we're trying to evaluate, but we still don't know this, because pi over 12 is not a special angle. Okay, so using this one here, the double angle, is not actually the way to go. Here's what we have. We have that pi over 12 is equal to pi over 4 minus pi over 6. Okay, think about it for a sec. If we times top and bottom by 3, top and bottom by 2, we get 3 pi over 12 minus 2 pi over 12. That is indeed pi over 12. So I can represent pi over 12 as a subtraction. I can say that sine of pi over 12 is identical to sine of pi over 4 minus pi over 6. And so therefore, that's identical to the sign difference identity. The sign difference identity says that sine of A cos of B, well, maybe I'll write it out this way, cos of B, I'll actually write the formula, minus cos of B sine of A. Okay, so where pi over 4 is my A and pi over 6 is my B, I have now that we have sine of pi over 4 cosine of pi over 6 minus, well, yes, I mixed that around. Sorry, this should be an A and this should be a B. So sine of pi over 4 cosine of pi over 6 minus cosine of pi over 4 sine of pi over 6 is what sine of pi over 12 equals. And these are all special angles. We can evaluate them. Sine of pi over 4, that's 1 over root 2, or root 2 over 2 if you prefer. Cosine of pi over 6, or cosine of 30, that's root 3 over 2. Minus cosine of pi over 4, that's 1 over root 2, times sine of pi over 6, that's a half. Okay, so now this is root 3 over 2 root 2 minus 1 over 2 root 2. And so we have root 3 minus 1 over 2 root 2. That is what sine of pi over 12 is. Or sine of pi over 12, of course, is half of pi over 6. So this is sine of 15 degrees. Sine of 15 degrees is exactly that there. That's an exact answer. That's pretty impressive. Of course, if you want, you could rationalize this. You could multiply top and bottom by root 2. If you wanted to rationalize it, you'd have root 2 onto root 3 minus 1 over 2 root 2 times root 2. That equals root 6 minus root 2 over 4. Okay, so that's an alternative expression that's identical to this one. But either way you slice it, that's what sine of pi over 12 is. That's kind of cool. Here's an example for you based on the same premise. Figure out what the exact value of tangent, I'll do this in degrees to make it a little bit simpler, tangent of 105 degrees is. Can you figure out an exact value for that? Think, how could you combine two special angles to get 105? Pause the video, try it out, and when you're ready, have a look at the video again and see if you got the same answer as me. All right, let's see if we got the same thing. So I said 105 degrees is 135 degrees minus 30 degrees. Those are both special angles. And then I took the difference formula for tangent, the difference identity. There it is. I substituted in a value of A equals 135 and B equals 30. And so tangent of 105 is tangent of 135 minus 30, which is tangent of 135 minus tangent of 30 over 1 plus tangent of 135 times tangent of 30. Great. Now I've got to evaluate these tangent values using special triangles. So tangent of 30, not so bad. I use a 30, 60, 90 triangle, and I get that tangent is 1 over root 3, opposite over adjacent. Maybe you've memorized it, but if not, you can get it from the special triangle. Tangent of 135, a little bit more work, but not so bad. 135 here, its reference angle is 45, right here. So I drew the 45, 45, 90 triangle, 1, 1, and root 2. And then I drew the corresponding 45, 45, 90 triangle in the second quadrant. And I made sure that my x value is negative 1. Okay, and so this gives me that tangent of 135 degrees is 1 over negative 1, which gives me a value of negative 1. So far, so good. Great. Okay, so now I can just plug in negative 1 and 1 over root 3 where they apply in this formula up here. So I have negative 1 minus 1 over root 3 over 1 plus negative 1 times 1 over root 3. There it is. Now it's a matter of simplification. So I factored out my negative 1. I got negative 1 onto 1 plus 1 over root 3 over 1 minus root 3, because this is just a negative. And then I went ahead and I simplified inside the brackets there. 1 is the same as root 3 over root 3. So I have root 3 over root 3 plus 1 over root 3, which is root 3 plus 1 over root 3. That's what this is. And the negative is still hanging out outside. The denominator, same thing, root 3 over root 3 minus 1 over root 3. This is root 3 minus 1 over root 3. That's that there. And then I have a fraction divided by a fraction. Well, I can do keep, change, flip. There they are as fractions. I put my negative out front as a negative 1. Take the reciprocal. My root 3's cancel out. And I'm left with this. That's a pretty good answer. I would be satisfied with that, but you might want to rationalize. If you want to rationalize the denominator and you have a binomial there, or effectively a binomial, you need to multiply the numerator and denominator by the conjugate of that denominator. That means you copy both numbers, but you change the sign to a plus in this case. So I'm going to multiply the numerator and denominator by the conjugate. and I go through my negative still there. Root 3 times root 3 is 3, plus root 3 plus another root 3, that's plus 2 root 3. 1 times 1 is 1. There we have our numerator. Root 3 times root 3, that's 3, minus root 3 plus root 3, those cancel out. And then I have negative 1 times 1 is minus 1. So that denominator just becomes a 2, which I decided to write as a half. My 3 and my 1 become a 4, and I still have my 2 root 3. I decided to factor out a common factor of 2 here. So we have negative a half times 2 plus root 3. And then these cancel. That's what gives me this final answer here. And if you go ahead and use a graphing calculator, here I'll pull up my GDC. Oh, it's not turned on. Hold on here. I'll pull it up here. Okay, so here's my graphing calculator. Now, this whole question boils down to negative bracket 2 plus root 3. So I'll type that in. Negative bracket 2 plus square root, that's second square root of 3. By the way, whoops, and by the way here, let's delete that bracket, come over here. Uh-oh. Here, let's just start again. Negative bracket 2 plus square root of 3, and I'm going to come all the way outside now to close my bracket. Notice that on your graphing calculator, negative and minus are not the same thing. So if you want to make something negative, you need to use this negative button down close to enter. If you're subtracting, that's different. Okay, so this is what I have. Negative 3.73. And recall that the whole question was having us figure out the exact value of tangent of 105 degrees. Okay, now my graphing calculator, it's actually, is it in degree mode? Let's go to mode. No, it's in radian mode. So I'll come down here and change it over to degree mode. And I'll exit that, second quit. And now I'm going to go tangent of 105 degrees. What do we get? Drum roll, please. Boom, we got it. Okay, so this exact answer, in fact, is even more accurate than what the calculator can give us because we have that square root 3 there. That's irrational. So we have the actual exact answer, and it matches. So we're in good shape. So here we are. Okay, so this is great. This gives us what we need to now tackle questions in the textbook from page 306, number 5, 7 to 11, 13 to 17 plus.